So, good morning, students, and welcome to the lecture. Here, last time we have derived the kinetic gas equation, and all of you know Pv it is equal to 1 by 3 m n u square. This is the kinetic gas equation. Okay, though it is obtained for a cubical vessel, it holds good for all shapes of containers. Okay, then the significance of the term u. As stated here, u square is the mean of squares of the individual velocities of all the n molecules of the gas, but u it is equal to square root of u square. Therefore, u is called as root mean square velocity or RMS velocity. The kinetic gas equation in terms of kinetic energy. Here we will see the kinetic gas equation in terms of kinetic energy. All of you know the kinetic energy, it is given by 1 half m u square, where u it is the velocity, and we have Pv it is equal to this 1/3 m n u square. It is the kinetic gas equation. So we modify this equation as, or we may write this equation as 2 by 3 n into 1 half m u square, and it is equal to 2 by 3 n into E, where E it is the kinetic energy, and we can write this equation as 2 by 3 into capital E, where small e is the average kinetic energy of a single molecule and the total kinetic energy of all the n molecules. Therefore, we can write Pv it is equal to 2 by 3 into E, and this expression with the general gas equation Pv it is equal to nRT, we can write 2 by 3 n 2 by 3 E it is equal to nRT for 1 mole of gas. The kinetic energy of n molecules it is given by here 2 by 3 into E it is equal to nRT, and since the gas molecules in 1 mole it is equal to Avogadro number, therefore we can write this equation as E it is equal to capital E upon N0. It is equal to 2 by 3 RT upon N0. This is the gas equation, kinetic gas equation in terms of kinetic energy. Okay, so let us begin with the new point, and that is the ideal and non-ideal gases. Here the ideal gases are those gases which obeys the ideal gas laws, and ideal gas laws are Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, Graham's law of diffusion. And remember well, the ideal gases they obey all these ideal gas laws at all conditions of temperature and pressure, and the gases which do not obey the ideal gas laws at all conditions of temperature and pressure, they are called as non-ideal gases or real gases. Okay, so let us see in short the ideal gas laws. The first law it is the Boyle's law, and the Boyle's law it is stated as the volume of given mass of a gas varies inversely as its absolute pressure, provided the moles and temperature remains constant. In short, the Boyle's law it is also states that the volume of any gas it varies inversely with pressure at constant temperature. That means there is an inverse proportion in volume and pressure at constant temperature. This is the Boyle's law. Then the Charles law. The volume of given mass of a gas varies directly as its absolute temperature, provided the moles and the pressure is a constant. Okay, this is the Charles law. There is a direct relationship between volume of a gas and temperature. Then the Gay-Lussac's law, the pressure of a given mass of gas varies directly as its absolute temperature, provided the moles and volume is kept constant. And Avogadro's law, for a given mass of an ideal gas, the volume and the amount, that means moles of gas, are directly proportional if the temperature and pressure are constant. These are the statements of ideal gas laws, and the ideal gases are the gases which obeys ideal gas laws at all conditions of temperature and pressure. And those gases which do not obey the ideal gas laws are the real gases or non-ideal gases. So here the ideal gases, they take up no space, there are no intermolecular attractive forces, particles are moving in a constant random motion, the collisions are elastic, there is no attraction or repulsion with the container, and it follows the laws under all conditions of temperature and pressure. These are the ideal gases and the saline features of the ideal gas. Then here we will see the distinguishing characters of ideal gases and real gases. All of you know the ideal gases obey all gas laws under all conditions of temperature and pressure, while the real gases obeys gas laws only at low pressures and high temperature conditions. That means the real gases they obeys ideally only at low pressure and high temperature condition. See L P H T, that means low pressure and high temperature. Real gases obeys the gas laws, ideal gas laws, or real gases they obeys ideal gas laws. Then the second characteristic or distinguishing point, the volume occupied by the molecules is negligible as compared to the total volume occupied by the gas in case of ideal gases, and in case of real gases the volume occupied by the molecules is not negligible as compared to the total volume of the gas. Then the force of attraction among the molecules are negligible, and the force of attraction are not negligible at all temperatures and pressures in case of real gases. Then here ideal gases obeys the ideal gas equation P it is equal to nRT, and the real gases they obeys the van der Waals equation, and in this chapter you are going to learn the van der Waals equation how it is derived. Okay, these are the some distinguishing points in between the ideal and real gases. Okay, then these are also the distinguishing points, and here the ideal gases, they are independent of the factors like temperature and pressure, and real gases, they interact with other gas at highly dependent. And again, ideal gases are hypothetical gases. They do not really exist in the environment, and the non-real gases, they are not hypothetical. They really exist in our environment. These are also the distinguishing points in between ideal and non-ideal gases. Then here at first we will see the deviations of real gas from Boyle's law. Deviations of real gases from Boyle's law. Already you are familiar with what is the Boyle's law. Okay, in case of ideal gases, the Pv, it is equal to constant at constant temperature. That means when we plot the graph of Pv versus P at a constant temperature, this Pv product, it is the constant, and this shows the nature of ideal gas. This is the deviation of ideal gas in case of behavior of ideal gas and real gases. Here in this diagram, this is the curve for CO2 gas. This is the curve for CO gas. This is the straight line above the ideal line for H2 gas, and this is for helium gas. Then the Pv values in case of real gases, they shows decrease in Pv value with increase in pressure. It reaches to the minimum and then increases with increase in pressure. Okay, instead of getting a straight line here, as we have obtained in case of ideal gas, the Pv values are constant at constant temperature. Either we increase the pressure, these values, they remains constant. Okay, but in case of real gases, the Pv values, they decreases, reaches to the minimum and then increases. This is the deviation of real gases from ideal behavior from the Boyle's law. Here, real gases do not obey ideal gas equation at all conditions of temperature and pressure. This can be understood from the graph Pv against P for different gases. For ideal gases, Pv is constant for any pressure. So, the graph obtained is a straight line parallel to the pressure axis, and for H2 helium, Pv increases with increase in pressure, and in case of CO and CH4, the value of Pv first decreases, reaches to a minimum value and then increases. Okay, then the reasons for deviation from ideal behavior. Why the real gases, they shows the deviations from the ideal behavior, and there are two reasons here. The first reason, the actual volume of the gas molecules is negligible as compared with the total volume of the gas, and there is no force of attraction between the gas particles or gas molecules. And these two assumptions, they holds good only in case of ideal gases, but these two assumptions are not true in case of real gases. And all of you know, the gas molecules are rigid and incompressible bodies. Though we decrease the pressure, their volume decreases, but it cannot be neglected in case of real gases. And again, there are attractive forces in between the gas molecules. They exert pressure on the walls of the container, and these two assumptions becomes wrong at a high pressure and a low temperature condition. And these two are the reasons why real gases, they shows the deviations from the ideal behavior. Here, the extent of deviation of the real gas from ideal behavior, it is expressed in terms of compressibility factor, and compressibility factor, it is denoted by letter Z. Here, the deviation from ideal behavior can be measured in terms of compressibility factor denoted by Z, which is the ratio of product of Phi and nRT, and mathematically Z, it is equal to Phi divided by nRT. Then for ideal gas Z, it is equal to 1 at all temperature and pressure. So the graph of Z versus P will be straight line parallel to the pressure axis. And in case of real gases, the value of Z, it deviates. That means it may be either less than 1 or greater than 1. The value of Z, it is either less than 1 or greater than 1 in case of real gases. This is the extent of deviation of real gas from ideal behavior. Then again, the volume of any gas at STP condition. The volume of any gas at STP condition, 1 mole of any gas, it has the volume 22.414 liters. Okay, the volume of ideal gas, 1 mole of any ideal gas, it has a volume sorry, 22.414 liters. But this volume in case of real gases, it may be either less or it may be either greater. Okay, due to the intermolecular force of attraction and the volume we cannot neglect. Okay, here the ideal gas, it has a volume 22.414 liter. In case of H2, this volume is 22.433. Helium 22.434. N2, this volume, O2, this volume. And you will see here all these values are less than the ideal value. and these values are greater than the ideal value. That means the real gases, they shows deviations from the ideal behavior. Due to these two assumptions, they are not hold good in case of real gases. Then again, this is the diagram of PP versus P, and it shows the deviation of real gases from Boyle's law. The next point we will see later on.